Now, welcome to this yet another particular lecture whereby we are going to handle the embryology of GIT. My name is Kipkoech Evans from Masinde Muliro University of Science and Technology, that is Kenya, East Africa. Now, today we are going to handle the development of GIT. The first objective is the esophagus. Second one is stomach. Third, large and small intestine, and finally we conclude with the congenital anomalies of each. Now, introduction. Tissues of origin of any GIT are derived from, the first one is the endoderm, the second one is the splanchnic mesoderm, and the neural crest cells. Now, the endoderm will give rise to the epithelial lining and the exocrine glands, while splanchnic mesoderm will give rise to the smooth musculature of the gut wall. It will also give rise to connective tissue elements and the mesentery when dealing with the intestines. The third one is the neural crest cells, which will give rise to enteric nervous plexus, whereby this enteric in physiology it's divided into two, that is the subcostal and the mesenus, or what you call the aureus plexus. Now, let's start with the first objective, that is the development of the esophagus. Esophagus is formed from the foregut segment of the primordial gut tube. So it's a foregut, it's one of the foregut derivative. The respiratory diverticulum forms from the ventral aspect of the foregut. So it begins with the formation of this respiratory diverticulum, which is formed from the ventral aspect of the foregut. This foregut then undergoes what you call septation. And how does it undergo this septation? There is formation of what you call a septum, that is tracheoesophageal septum. And this tracheoesophageal septum is formed by growth of tracheoesophageal ridges on either side of the lumen and fuses in the middle, forming a groove-like structure called the tracheoesophageal septum. And this tracheoesophageal septum will now divide the lumen into the anterior, which will become the trachea, and the posterior part, which will become the esophagus. Now, after septation, we move to elongation. This lumen must elongate to gain its normal length. So the esophagus segment undergoes elongation process, and due to this elongation process, it will push the diaphragm, so it will descend the diaphragm. Now, from the fact that we know that the inner parts of this lumen is lined by endodermal cells, there is rapid proliferation of these endodermal cells. And what is the conclusion? This rapid proliferation of the endodermal cell will cause obliteration or occlusion of the lumen. So due to rapid proliferation of the endodermal cells, the lumen will become obliterated, resulting to what we call the solid stage development. Now, we want to regain the luminal part of this developing this future esophagus. So the final stage is the recanalization process, which normally occurs at the 10th week of intrauterine life. And this recanalization occurs through what we call the factualization, that is formation of factuals. Let me show you the slide of the development of esophagus. So the embryonic origin is the foregut. Tissues of origin, there are three: splanchnic mesoderm, endoderm, and the neural crest cells. Developmental stages. We've said that it is formed from the foregut segment. That is the basic knowledge. Then the second thing we talk about, that respiratory diverticulum, which is formed from the ventral aspect of the foregut. The third thing is the septation, which occurs by what you call the tracheoesophageal septum. And then we have elongation. elongation is just that extension of the lumen towards the lower parts of the abdomen. And the effect of this elongation, it will cause the diaphragm to descend. Now let's continue. Now so the fourth thing is that rapid proliferation of these endodermal cell layers on the walls of this lumen, leading to what we call the obliteration of the lumen, resulting in what we call the solid stage development. And the last thing is the recanalization process, which occurs at the 10th week of intrauterine life. Now let's flip the coin and move to the second objective, that was the development of the stomach, or what you call the embryology of the stomach. Now the stomach is formed from the foregut of this, but is the distal part of the foregut. Now this stomach begins as a fusiform dilatation in the distal parts. So this fusiform dilatation now grows, the posterior border of this dilatation grows faster than the anterior border, leading to formation of curvatures. That is the greater curvature to the left in the posterior, and the lesser curvature on the anterior part. So the anterior border becomes the lesser curvature, and the posterior border becomes the greater curvature. Let me show you the slide of that. After formation of the lesser and greater curvature in what you call differential growth, it then undergoes rotation around both vertical and anterior posterior axis. So there are two types of rotations, that is vertical rotations at an angle of 90 degrees and anterior posterior axis rotation at an angle of 60 to 70 degrees. Let's start with the first one, that is the vertical rotation. At vertical rotation, this dilatation rotates in 90 degrees clockwise. Now let's continue. So I had begun with the first one, that is the vertical rotation, which we've said that it occurs at around 90 degrees clockwise, pertaining the position at which you are viewing. But let's just take that it is 90 degrees clockwise. Now the effect of this vertical rotation are the following. Now it will cause the changes in gastric surfaces. What do I mean by this? These gastric surfaces are just the lesser and greater curvature, whereby the greater curvature will move to the left, while the lesser curvature will move to the right. Number two, it will cause the right vagus nerve to become the posterior vagal trunk, while the anterior vagus nerve will become the anterior vagal trunk. The third effect is that the ventral mesogastrium goes to the right, forming omentum, carrying with it the future liver, that is the liver bud. The dorsal mesogastrium goes to the left, carrying with it what will future form the spleen. Now let's move to the second rotation, that is the anterior posterior axis rotation. I told you that this rotation occurs at about 60 to 70 degrees Celsius, 60 to 70 degrees, and it is also clockwise direction. And the effect of this 60 to 70 degrees anterior posterior rotation, it will push the fundus slightly upwards, and pylorus, it will push the fundus slightly downwards, and pylorus slightly upwards. I think that's the only effect of this anterior posterior axis rotation. And that is the formation of the stomach. So in summary, we begin that it is formed from the distal part of the embryonic foregut. Then we say that it begins as a fusiform dilatation in the distal parts of the foregut. The third thing we say that the posterior border of this dilatation will grow faster than the anterior border. And the effect of that is that it will cause the lesser and greater curvature. The fifth thing is that it will undergo rotation, which is both vertical and anterior-posterior axis rotation. Now, we can flip the coin and move to the third objective, that is the development of the large and small intestine. Now, this one occurs concurrently. So, large intestine is developed from predominantly the midgut and the hindgut, while the small intestine, the first part of the duodenum, that is D1, is obtained from the foregut, that is D1 and half of the D2. Those are parts of duodenum, while the rest part of the small intestine, that is jejunum, ileum, and the other parts are derived from the midgut and hindgut predominantly. Now, small intestine are derived from the incorporated part of the yolk sac, that is the primordial gut tube. The first part and the upper half of the second part of the duodenum is derived from the foregut. Yeah. Now let's move to the developmental stages. The first thing, you deal with what we call the rapid proliferation of midgut will lead to elongation and formation of coils, and these coils are what we call the intestinal loops. So we've said that the rapid proliferation of midgut will lead to elongation and formation of coils, and these coils are what we call the intestinal loops. Now, the apex of the loop is attached to the involuting yolk sac via what you call the vitelline duct, forming what you call the cephalic and the caudal limbs. The cephalic limb will predominantly form the small intestine, while the caudal limb will predominantly form what you call the large intestine, or what you call the colon. The third thing is that this loop herniates through the umbilicus. Umbilicus is that opening which will become the future navel. And why is this loops or these coils herniating out of the umbilicus? That is for the purpose of achieving more space for further development. This herniation normally occurs at 6th week of intrauterine life. I know you are wondering why these intestines, the reason for them to herniate out is because of the small space of the fetus. And what causes this small space? Due to the larger size of the liver, and also the larger sizes of kidneys will accumulate most parts or most of the space in the abdomen. This process of herniation is what you call the physiological umbilical herniation, which occurs at the 6th week of intrauterine life. During this herniation, during this exit of these coils of intestine, there is a rotation of 90 degrees. And this rotation is what you call the external rotation. Why? This is because it occurs outside the fetus. At the 10th week of intrauterine life, these coils, these intestinal loops, return back in what you call the hernia reduction. That process is physiological hernia reduction, with the duodenum being the first one to return. And during the return, the large gut rotates another 180 degrees in anticlockwise direction. Now, why are these coils returning? This is because at around 10th week, the abdominal space will have become a little bit larger to accumulate these intestinal loops and other abdominal viscera. Now, what contributes to this greater space of the abdomen? This is because of the reduction in the left lobe of liver. I know that you've seen that the left lobe of the liver is a little bit smaller in size than the right lobe. This is because of the reduction in its production or its homopoietic or production of blood. We know that liver produces blood at the fetal stage. This is because the bone marrow has not yet been formed, or the ossification has not yet begun. Now, we've said that during the return, the large gut rotates another 180 degrees. Now, what is the effect of this rotation of 180 degrees? This 180 degrees will cause the colon or the large intestine to accumulate on the peripheral ends of the abdominal space. That's why we see that the large intestine occupies the peripheral ends of the abdomen, while the small intestine is in the central position. Now, the final thing is what you call the fixation. Now, the gut is then fixed by regression of the dorsal mesentery derived from the peritoneal folds. And that marks the end of the development of large and small intestines. Now, summary. Site of origin is the distal foregut, midgut, and the hindgut. Tissues of origin, that is the endoderm, splanchnic mesoderm, and the neural crest cells. The third thing, we'll talk about the rapid proliferation of this lumen. And what is the effect of this rapid proliferation? It will cause elongation and formation of primary intestinal loop. Now, the fourth thing is what you call the physiological umbilical herniation. And during this physiological umbilical herniation, there is an external rotation of 90 degrees clockwise. The sixth thing is what you call the hernia reduction, whereby during this reduction, which occurs at the 10th week, there is internal rotation of 180 degrees, which normally occurs predominantly on large intestine. And the final thing is the gut fixation. Now, this marks the end of development of large and small intestine. Now we can flip the coin and move to the congenital anomalies of these parts of GIT. Before that, let me show you the slide pertaining the development of large and small intestine. Now, this is the slide which will accommodate the development of both large and small intestine. So the key things here are the periods of physiological umbilical herniation and what you call the hernia reduction. Now we can flip the coin and move to the congenital anomalies of different parts of GIT. We can start with the small intestine. We have some congenital anomalies. The first one is what you call the omphalocele. Let me show you the slide. This is the continuation of development of small and large intestine. Now, the first one is the omphalocele. Omphalocele is caused by failure of the umbilicus to close completely, causing the abdominal contents to herniate outwards. And these contents are mostly covered by a membrane. This is what you call omphalocele. This is the picture representing this anomaly called omphalocele. It appears so frightening, but you can just view it. So omphalocele is caused by failure of the umbilicus to completely close during that hernia reduction and hernia and the herniation, physiological herniation. And the coils of the intestines are covered by a membrane, so they are enclosed in a sac-like structure called a membrane. Now we can move to the second, that is the gastroschisis. Gastroschisis is this one whereby, so the difference between, do you see the difference between omphalocele and gastroschisis? Yes, there is a difference. The difference is that omphalocele is covered by a membrane-like structure, a sac-like structure called a membrane, while gastroschisis is the coils are just exposed anyhow. And the coils of gastroschisis normally lies at the right part, while the coils of the omphalocele normally occupies the central position of the abdomen. The third one is the congenital umbilical hernia. This congenital umbilical hernia is caused by the incomplete closure of the anterior abdominal wall after this gut has returned into the abdominal cavity. So it is caused by the incomplete closure of the anterior abdominal wall after the gut has returned to the abdominal cavity. There are so many anomalies. We also have what you call the intestinal atresia. What is atresia? Atresia is the obliteration of the lumen, or is the complete blockage of the lumen, maybe caused by the failure of recanalization, since we know that before that there was a solid stage that is caused by rapid proliferation of endodermal cells. So that is what you call the intestinal atresia. We can also have what you call the duodenal atresia. Duodenal atresia is the complete blockage of the duodenum, also caused by the same reason, that is the rapid proliferation of endodermal cells with failure of recanalization process at the 10th week of intrauterine life. Those are some. There are so many anomalies, but for now we can have those. I think there are 7 or 6 there. Now we can also have what you call the congenital anomalies of the stomach. Number 1, we have the midgut malrotation. Midgut malrotation is just maybe there is a malrotation or a failure of any rotation. We said that there are 2 types of rotation. That is the vertical rotation at 90 degrees and anteroposterior axis rotation at 60 to 70 degrees. So due to maybe there is a malrotation, maybe the 90 degrees, the vertical rotation failed to occur. Therefore, it will lead to some malfunction on parts of the small intestine. You can also have what you call the aganglionic megacolon. Ganglionic megacolon is that the overbulging of this distal parts, or what you call distal part of the sigmoid colon. And at this distal part, there are no ganglion cells. The area is affected by what you call the Hirschsprung's disease. So a ganglionic megacolon is typically what you call the Hirschsprung's disease. Now, up to that point, I think we are done with today's objective. Now, the next objective is that I know we didn't handle the congenital anomalies of the esophagus, but we will just handle it in the next lecture. Up to this far, I thank you for your cooperation, and we continue to learn together. My name is Kipkoech Evans from Masinde Muliro University of Science and Technology, that is Kenya, East Africa. Thank you for your cooperation.